today. So, toward the end, getting toward the end of chapter 12, we run into 12.5, and there's the big idea in 12.5 is this concept of curvature. Now, actually, though, the way the book presents this material, I'm going to do it like the book, and so it'll take me a little while to get to the topic of curvature. So we start with this other topic. We start with this topic of arc length. And arc length of a curve is represented with the letter S, the little s. And the arc length formula for, and you may recall some of this from Cal 2, you did an arc length maybe, but in Cal 3, here we're dealing with these vector valued functions, and the arc length formula is this. It's an integral, it's an integral from A to B, and we are integrating the magnitude of r prime of t with respect to t. So, oh, the other thing I mentioned Monday, and I'll mention now again, we're getting a lot of formulas in this chapter. There was a bunch of them Monday, and there's more today. So there's a lot of formulas in this chapter, and you don't have to really memorize any of them. I'm going to hand them to you for the purposes of the test. Well, maybe even the quiz in some respects. But so I'm going to give you a formula sheet. So we're not memorizing formulas, but we got to understand them and work with them. This is the arc length formula to find the length, like if you, on these curves, and they can be in 2D or 3D, but on these curves, if you lay a tape measure on the curve and measure its length, that's what this does. Let's do one. Let's do r of t, let's do a nice helix like this. 3 cosine 3 cosine 3t, comma 3 sine 3t, a lot of 3's in there, and comma 4t. So by the way, that is a helix. We kind of learned that back in 12.1. Helix, radius 3, circular motion in the xy plane, rising up out of the xy plane, rising up in the z direction in some linear fashion, I guess. It's got a radius of 3. The period is also adjusted. Let's just real quick, what is the period of this helix? In other words, what's the time it takes to get one lap around?
2 pi over 3.
It is 2 pi over 3. That's how you calculate the period. So if I'm asking, I wanted to calculate the arc length of this, I need to ask a question. I mean, how much of the arc length do I want? So maybe I want to say this. I want the arc length. I want the arc length of one lap, of one revolution, or one lap around, or one revolution of this helix. So when I ask that like that, that's not telling you, oh, you mean from 0 to 2, or from 0 to 3, or from 0 to 2. I mean, I'm not telling you the time. I'm asking for one revolution, and then it's up to you to calculate the period and realize that you'll probably integrate this from, bless you, you'll probably integrate this from 0 to 2 pi over 3, right? Don't you think that'll take care of one revolution?
Yeah.
Okay. By the way, we're doing this with respect to t. The bounds are t values. Everything's with respect to the variable t, or the parameter t. Okay, well then I need the magnitude of r prime of t here. You know, I sort of feel like I should go work out to my scrap paper and work on that. First of all, I need r prime. Let's go over here where I got a little room. I need r prime of t. I need r prime of t, which is the derivative, which is the derivative of cosine is negative sine, but the chain rule is going to spit out a 3, negative 9 sine 3t. Are you guys okay? Then the derivative of the sine is cosine, chain rules, so 9 cosine 3t. and then comma 4. And now I need the magnitude of that. I need the magnitude of that, and then that's what I'm going to integrate. But before I stick it in the integral here, let's just do it over here on my scrap paper. I need his magnitude, the magnitude of r prime. And that's in general, so here it is. It's the square root of, you know how to do a magnitude, I guess, him squared plus him squared plus him squared. Watch this. If it's him squared, that's 81 sine squared 3t. That's 81 cos squared 3t. And that's 16. And this happens a lot. I don't know how much homework you've done or what you've run into, but when you're messing around with these helixes or this circular motion, and anyway, you get this sine squared plus cosine squared in here. Now, the way to finish this appropriately here is to factor out the 81, just out of those two, of course, not the 16. And then you're left with sine squared 3t plus cos squared 3t plus 16. This is
1. Yeah.
1, thank you, that's a 1, but it's multiplied by the 81, so this is actually just an 81 plus 16. I mean, the 1 is multiplied by the 81. You factored out the 81. This is a 1 times 81 plus the 16, so there we are. This is the square root of 97. And then, to find his arc length, I'm integrating the square root of 97 with respect to t. I mean, to finish this integral is going to be real easy because it's a number. And I mean, that's why I picked the helix like this, because it came out to be a constant. Let's just talk about this just a second before I finish the problem. What does this mean? I took the derivative, which is the velocity vector, and I guess at any time, I didn't do this at a specific time, I did this at any time, I guess the length of the velocity vector is that, which means there's no t's in there, it's constant. So you're on this helix, you got a constant velocity. That's the wrong word. Because the velocity keeps changing direction. So you don't say it has a constant velocity. The velocity has a constant magnitude. The length won't change. The direction changes. So you can't say the velocity is constant if the direction is changing. But the length of the vector is not changing. The length is constant. I guess the word is the speed is constant. The speed is constant. So you're traveling around this helix. There's a velocity vector at any place, but all those velocity vectors have the same length. Square root of 97. To calculate the arc length from 0 to 2 pi over 3, and that's the arc length of the curve, you do this integral. I didn't explain that. I didn't prove to you why this is arc length, but this is arc length. When you integrate with respect to t, you get the square root of 97 times t. You integrate, you evaluate from 0 to 2 pi over 3. You stick in your 2 pi over 3, and this is your arc length. I mean, that used to be my number on the Minnesota hockey team. No, I'm kidding. That's the arc length. Roughly, that's a 10, if you agree with me, and that's roughly 20. You can sort of cancel the 3 with the pi, sort of. Anyway, I'm saying that's roughly the number 20, 22, 21, 23. It's a length. It's a length.
Yeah, it's 20.6.
20.6. Yeah. I just was estimating it in my head there. So, but it's a length. Cool. Just real quick, I don't know, can we draw this little guy? He has this, he's a space curve. He's a helix. He has a radius of 3. He starts here on the x-axis at 3. I know that if I plug in a 0, those are zeros, and that's a 3. So he starts there at t equals 0. He goes around this way, and he goes around, and he's doing his helical motion. But when he comes around one time, he's right above where he was before, and we just found that length of that curve. That's what we just found. Yeah. So we're starting with this topic of arc length. We are, this is not the biggest topic in the world, but I got more to say about it. But it's building toward a bigger idea called curvature. So we'll get there. But right now I'm just measuring the arc length of a curve. So next the book does this. This is kind of subtle here. Watch this. They talk about the arc length as a function. So I guess I'm going to call this the arc length function. Now watch how I do this. So instead of a number like 20, okay, this is going to be the arc length function. So here it's going to be s of t. It's going to be a function of t. It's going to be s of t, and then here's what it is. It's an integral from 0 to t. And then if I got a t, a variable t in my bounds, anyway, I can't have this variable be t. So I'm just going to change this variable just because I can't let it match that variable. So I'm going to call this, it's the same formula, but I'm going to call it r prime of u du. Now, so what are you going to do? You're going to do the same thing, except when you integrate, instead of plugging in real numbers like I did, after I integrate, I'll be plugging in a variable t. And so I won't have a numerical number answer. I'll have an s of t. I'll have, how does arc length relate to time? How does s relate to t? I'll have s as a function of t. Now, so let's just do this. So on this problem, okay, what would change? Okay, I'd be trying to do this. I'd be going like this. I would do this integral from 0 to t, and then I'd do this, okay? So maybe I would, technically, I got to sort of change the variable from t to u. Now, I'm not going to do that. Hang on. I would do his derivative. I would do his magnitude. What did all that come out to be? Square root of 97, right? Same, I'm doing the same problem, except instead of concrete bounds, I'm doing this variable bounds. And so now I'm still going to integrate the square root of 97. Now technically now I'm going to put a du here. And so now let's do this problem. Watch. When you integrate the square root of 97 with respect to u, you get the square root of 97 u, of course. You're going to evaluate from 0 to t. So what are you going to plug in for that u? You're going to plug in t. And then a 0, but the 0 will just go away. And so when I plug in the t, I have this. S of t equals the square root of 97 times t. And this is the relationship that exists between time and arc length on this particular helix. On this particular helix, every 1 second I travel the square root of 97 feet. The truth is there's no units on this. This is a math problem without units. But if I wanted to think of it like that, t is time in seconds and arc length is distance in feet. If I wanted, then that's true. Every 1 second I travel square root of 97 feet. After 2 seconds, such and such. After 3 seconds, such. So I have this relationship between length traveled and time traveled. What we do with that is this. So now I'm gonna, so with that arc length function, I do this funny thing. You ready? I'm gonna add asked this question. The book asked this just a couple times. I've got this maybe on my take-home quiz. You might see this. I want to reparameterize the curve. And by the way, that's the curve. I want to reparameterize the curve in terms of the arc length parameter S. Okay, reparameterize the curve in terms of the arc length parameter S. I mean, this sounds like an episode from Star Trek. Yeah. And so right now, you know, you have this curve and it's parameterized in terms of t, okay? But hang on, I want to reparameterize it in terms of s. So what is the relationship between s and t? Well, we calculated that. The relationship between s and t is this. And let me just say it a different way. S is the square root of 97 times t. So now, what is t? T is S over the square root of 97. So here's what you can do. You can go to all those t's and you can replace them with S over the square root of 97. And then what you'll have is this curve. This is the same curve, but it won't be R of t. It'll be R of S. And I'm going to go to this curve, and everywhere I see a t, I'm going to replace it with S over the square root of 97. It's the same curve. What am I doing? I'm replacing that t with S over the, so I'm going to get 3S over the square root of 97, comma, 3 sine 3S over the square root of 97, comma, 4 times t, which is 4 times S over the square root of 97. Look at that, I don't know. I think it's kind of cool. But that's me. I like all kinds of math. And you've reparameterized the curve in terms of its own arc length. Now, you know, what's it good for? Well, like I said, it leads to a discussion on curvature. We'll get there in a minute. You know, what is it good for now? Well, let's see. We're traveling along this helix, and the parameter is t, which I could think of as time. Now I'm still on the same helix, but my parameter is s, its own arc length. So anyway, watch this question. Where are you? What is your position? What is your position after traveling for 2 seconds? Well, I think you would plug in a 2 for t, and you could plug that in there, and you could find your position when t is 2 seconds, or after you've traveled for 2 seconds worth of time. Listen to this question. What's your position after traveling for 2 feet? Well, then I think you would plug in a 2 for s in here. This is a position function. It's a helix. It's a position function given the time traveled. This is a position function of the same damn helix, but given the distance traveled. So, find your position after traveling 2 minutes or seconds, you plug a 2 in there. Find your position after traveling for 2 feet, you plug a 2 in here for s. You guys all right? So that's one use of it. Instead of time, its parameter is s, arc length. It's arc length parameter s. Hey, let's calculate his r prime of s. Oh, geez. Do I really want to do that? Maybe. Let me try this. R prime of s. Now this is weird. I mean, I don't think I want to call this velocity. I mean, velocity is distance over time. When you take the derivative with respect to time, that's velocity. When I take the derivative with respect to its own length, I'm not really sure what to call it, but I'm going to do it anyway. And I'm just doing it for fun. Look, I don't need R prime of s anywhere. I mean, I want to show you something. I think this is always true. I'm going to find R prime of s. Let's see. Okay, that means I got to do the derivative of cosine again. Of course, that's negative sine. Wait a minute. When I do this with respect to s, hold on now, it's going to spit out, what's it going to spit out?
3 over square root.
3 over the square root of 97. Thank you. Out front times that other 3 would give me 9 over the square root of 97. Thank you. Comma. When I take the derivative of sine, it's a cosine, but it's that same game. It's going to spit out, the chain rule is going to spit out 3 over the square root of 97 times that 3. I'm going to get 9 over the square root of 97 out front here, comma. Let's take that derivative with respect to s. It's 4 over the square root of 97. So that's my R prime of s. Here's the trippy thing. Watch this. I want to do the magnitude of R prime of s. And I think I read this in the book. I think no matter what the curve is, the magnitude of R, when you reparameterize it in s's, take its derivative and find its magnitude, you always get 1. I'm not sure why or even how much I want to think about that. But I think it's true. Let me try it. How do I do his magnitude? Well, of course, it's the square root of this thing squared. Holy all right, if I'm squaring this thing, isn't that 81 over 97? That's pretty easy, actually, right? Sine squared of this stuff. Okay, cool. Plus, what if I square him? That's 81 over 97. Co-squared. And what if I square him? Is that 16 over 97? That's 16 over 97. Okay, awesome. All right, you know the game because we just played it over there. You know the game. If you factor out, I'm in that square root, I just erased it. But if you factor out that square root, if you factor out that 81 97ths, just out of those first two terms, you have a sine squared plus a co-squared, so that's a 1. Don't forget you have this 16 97ths over here. But that's a 1 times this. You gotta make sure you understand this algebra here. I've seen students screw it up. It's a 1 times this, so I'm left with 81 97ths plus 16 97ths. Dude, 81 plus 16 is 97 97ths, which is a 1. Can you tell me the square root of 1? Actually, no. It's the positive square root, so it's just a 1. Anyway, again, I don't have a good feel for what this means. It's the derivative with respect to s. It's not the derivative with respect to t. Is it even a tangent line? I don't even know if it's tangent. I might want to read up a little more about that. But it doesn't just happen with this problem. I think with all problems, when you reparameterize in terms of s, take its derivative and find its magnitude, it's always a 1. All right, I might be kind of done with arc length, maybe. So we have this discussion on arc length. You can calculate an actual arc length between 2 times, but you can also do this arc length function that helps you reparameterize the curve. Okay, so there's that. Okay, all right. So then that leads me to my first definition of curvature. Curvature is represented with this capital letter K. That's curvature. And there's about 5 or 6 formulas. Remember, there's a bunch of formulas in this chapter, and I'm going to let you have these formulas. So there's 5 or 6 curvature formulas, depending on the context of what we're working with. The first one, though, is this one. It's the magnitude of dt ds. So if I would have walked in and started talking about curvature first thing you would ask me is, what the hell you mean? What's that S? Where'd that show up from? But now you know, I had to have this 30-minute discussion on arc length. S is arc length. Now, what is capital T? Well, you learned that Monday. Capital T is this unit tangent vector. But it was always T of T, at least on Monday it was T of T. Apparently now, it's written in terms of S. I mean, I must be dealing with a unit tangent vector that's in terms of S. So behind the scenes, somebody took an R of T, reparameterized the curve, made it an R of S, and then they calculated capital T of S. Oh, and then they want me to do dt ds and find its magnitude, and that's what curvature is. Jesus. I mean, it's all very abstract, right? It's very abstract. Let me I think I'm going to come back to them. I can explain. I like that little formula. It's not actually a very useful formula, but I want to explain it to you. Let me tell you this about curvature. Here's this tells you about curvature right here. You ready? Watch this. So here's a curve. Okay? And when we talk about its curvature, it's almost like its slope in a way. It's not slope. But what I mean is that you can talk about its curvature at any point. So, way out here, like at this point, on that point on this curve, this is a curve, but at that place, it sure looks pretty straight. And so I would bet you calculate the curvature at that point and it's practically nothing, just because it's very darn straight. So you calculate the curvature here and you're going to get some curvature. And one way to think about curvature is it is the reciprocal of the radius of curvature of the best fit circle that fits there. Right, hold on. Now that's loosely, I'm going to loosely define that. What the hell did I just say? The best fit circle that fits at this point. That's, I mean, it's kind of like maybe the tangent line idea, but I'm going to try to, what's the best fit circle that sort of fits this curve at this point? And then whatever its radius is, the curvature is the reciprocal of that radius. So whatever the best fit circle is, so if it's a big circle, hang on, if it's a big circle, it's got a big radius. If it's got a big radius, the curvature is small. Did you follow that? I mean, if it's a big circle with a radius of 10, then the curvature is 1/10. The curvature is small. But over here, look, now this is, if I was to draw the circle that best fits right here, I think it would sort of be a small circle. A small circle with a smaller radius. A smaller radius is a bigger curvature. I mean, it's that reciprocal relationship. Thank you. Right, so the bigger radius is it happens at the less curvy part. The smaller tight radius happens at a very curvy part. So that's big curvature, that's little curvature. Right. So there's an idea. That's a cool idea about curvature. That's a cool idea, but you don't really calculate it like that. You don't really calculate this circle and then go find its radius. I mean, this is not very functional. It's very nice and conceptual, but you don't really work with that. I mean, it's a nice concept to have, but you really got another formula. Okay, so now curvature is this measurement of how curvy it is, I guess, at a certain point. Listen, so now let's go back to this. I want to talk about this. Let me talk about this. Boy, oh boy. So here's what this is. This is the rate of change of the unit tangent vector with respect to arc length. I mean, I'm reading this math, and capital T is the unit tangent vector. Okay, so if I'm going around this curve, here's a unit tangent vector. When I say unit tangent vector, that means, this was from Monday's class, a unit tangent vector has it's a unit vector, so its magnitude is 1. Now that's my unit tangent vector. Now as it moves around, it's a unit tangent vector. So is it changing its length? Is it changing its length? And the answer is no, because it's a damn unit vector. It's always length 1. So it's this unit tangent vector. It's not changing length. So hang on. It's the rate of change of the tangent vector. All right, listen to this. It's the rate of change of the tangent vector, but it ain't changing length. So what's it changing? Direction. Yeah, I mean, it's changing direction. And what this is measuring is how much is it changing direction over a certain length. So if it changes, so there's S. So if it changed a lot of direction in a short little s, that's big curvature. Whew. I mean, I'm explaining, this is tough, but I'm explaining the hell out of this math, this language. I'm interpreting this language. It's like Spanish. That's math. Right, it's not Spanish. Okay. But did you hear what I just said? I'm trying to make sense out of this for you. And I'm trying to say it's the rate of change of the tangent vector, which ain't changing length. So it's about the directional change of the tangent vector with respect to how far it travels. So if it changes direction in a very short little traveling distance, that's a hell of a big curvature. And then it's the magnitude of that change. It's the magnitude of that rate of change, and that's your curvature. So I tried. I'll tell you what. Again, not a real necessarily functional definition. I mean, you could do this if you were given your vector valued function in terms of S. I would use this. Maybe I would use this formula. But you know, we're often given, you know, all chapter we've been given our vector valued functions in terms of T. You know, if we want to reparameterize in terms of S, then I could use this. I mean, that's a lot of work. If I'm given it in R of T, there's a formula for that. It probably can be derived out of that, but here it is. I'm just going to tell you what it is. I'm at the end of 12.5 where I get all these fancy formulas, and if I'm given an R prime of T, ooh, this is it. This is the formula for curvature. It's R prime of T. If I'm given an R of T, it's R prime of T, cross product R double prime of T, the magnitude of that all over, this is why I want to give you these formulas and not make you memorize them, R prime of T cubed, the magnitude of R prime of T cubed. Wow. There's a formula. If you're given this, then I think I'd use this formula, which your book says is equivalent to this, the magnitude of T prime of T over R prime of T. Huh. Well, okay. Again, there'd be a lot of fun math proving why this is the same as this or why this is the same as this. I'm not doing that fun math. I'm just writing down some formulas. You don't have to memorize these formulas. They're all, these chapter 12 formulas are all summarized well at the end of chapter 12. Here's the truth, you guys. I've written down all these curvature concepts here now. The truth is, when we get to the topic of curvature, sometimes I revert to good old I go back to our good old y equals f of x days. So I know we're in this chapter where we're dealing with these space curves and these vector valued functions, but now that I'm into this topic of curvature here at the end of this chapter, sometimes I like to just go back to good old y equals f of x, which is just 2D, you know, in the plane. And here's the formula for curvature now. It's the absolute value of y double prime over 1 plus y prime squared, all to the 3/2. So there's the formula for curvature when you just got y as a function of x. Like I said, there's a bunch of formulas for curvature. I've just written down one. You can count that one maybe. 2, 3, 4. Yeah. But let's do a problem. Find the curvature of f of x equals negative 3x squared plus 8x minus 5. Let's find the curvature. Now, again, this curvature can be calculated at a particular point. I guess I didn't ask that. I guess when I asked for the curvature here, I guess I'm just doing it in general at any point. But this is my function, and so according to this curvature formula, this is my new cool curvature formula. If I have y just as a function of x, I need, well, you know what I need. I need y prime and I need y double prime, and then I need to fill in this formula. Okay, help me out. What is y prime?
Negative 6x plus 8.
Thank you very much. And then what is y double prime?
Negative 6.
Negative 6. And so here we go. My curvature formula is the absolute value of that negative 6, which actually I could call 6, over parentheses 1 plus the derivative. There's my derivative, negative 6x plus 8. That derivative gets squared. I don't think I want to FOIL it out, but it's the derivative squared plus the 1, and then all that to the 3/2. Wow, that's my curvature function. Can I write it any cleaner, any better? Not much. Like I said, though, the absolute value of negative 6 is, there's no argument, it's clearly a 6. I just said I didn't want to FOIL that out, but maybe I will for fun. If I do FOIL that out, I'm going to get a 36x squared and negative 96x, I think, and a plus 64. But then that plus 64 is going to be plus this 1. So I'm going to put plus 65. And then all that to the 3/2. Did you follow me on that? Mm-hmm. I FOILed the binomial, and then I added the 1 just to that term, and then I got all that to the 3/2. So maybe that looks a little better. I don't know. I'm not necessarily interested in you doing that algebra. It didn't help that much. You know, now I got a curvature formula, so I can ask questions like, I guess I did ask a question, find the curvature of this function, but I guess this question was find the curvature at any x, and that's what I got, the curvature at any x. You know, here it is again. So, but if I said, well, I want the curvature when x is 1, well, you can tell me what the curvature when x is, then you plug in a 1. Let's just find that. What is the curvature when x is 1? The curvature at x equals 1. It would be, well, I could plug a 1 in there, right? I could plug a 1 in there. I'd just soon go here, right, you guys? Screw this yeah, why did I do that? I want to go right there. If I plug in a 1, that's negative 6 plus 8, that's 2. 2 squared is 4. 4 plus 1 is 5. So I get a 6 over 5 to the 3/2, which, what is that? It's it's the square root of 5 cubed. I mean, it's 6 over 5 square roots of 5 is what it is, but I'm asking for a decimal.
0.54.
0.54? Okay. Okay, 0.54 he's saying. Thank you. That's my curvature at this point. Can I take a look at this? What is this? What is this? I want to take a look at this. This is a parabola. It's got a y-intercept of -5. It's upside down. Where is it? You guys know how to find the vertex of a parabola? In calculus, you find the vertex of a parabola. The vertex of a parabola is when the slope is 0. The vertex of a parabola is when it has a maximum, or when the tangent line has a slope of 0, or when the derivative is 0. So I'm just going to set this equal to 0 for a second, because this is my old, and I'm going to find out where this is. That's 8 over 6, -8 over -6. 8, that's 4/3, I guess. When x is 4/3, we're at our peak. Okay, cool. That's nice to know. When x is 4/3, we've reached a maximum. I'm not sure where we are, but this, I'm suggesting now that this is my parabola. Oops. It's an upside down, kind of skinny parabola, and I think the vertex happens at 4/3 there, according to my old calculus knowledge. What am I asking for? I'm asking for the curvature when x is 1. Well, when x is 1, I was, you know, let me say this again. Look at this parabola. These parabolas are, you know, if you just look at this leg of a parabola, it looks like a damn line. Hang on. It looks like a line, so it's not very curvy, okay? Right? It's not, it ain't got hardly any curvature. Hardly any curvature, hardly any curvature, hardly any curvature. I mean, it only starts to have a little curvature kind of up here. And I think it has its most curvature probably right up there at the peak. That's probably where it has maximum curvature. But I didn't ask for that. I asked for the curvature at 1, which is kind of right close to that. And so the curvature at 1 was kind of big. I mean, I don't know if you call that big or small. It's all relative. But at 1, that's the curvature, I guess. It's not the y value, it's just the curvature. I think it's got its max curvature at 4/3. Let's just see what that would be. How would I do that? Let's do the curvature at 4/3. That means plug 4/3 into the curvature function, which you have right here, but I don't want to do that. I'd rather do it right here. Look how easy this is. When you plug in a 4/3, well, if you remember, that's the number that made my derivative 0, right? And that's my derivative right there. So when you plug in the 4/3, it's -8, it's 0. Plus 1, which is 1, to the 3/2, which is 1, all underneath a 6. I think the curvature at 4/3 is 6. Damn, that's pretty damn curvy. I mean, this is kind of one of these skinny parabolas, and so right there at the top, it's got this kind of sharp turn. Well, not a, but it's yeah, right there the curvature is 6. Right over here the curvature was 0.54. Huh. There's some cool questions about graphing the curvature function. And if you, which is kind of tough because you've got to graph this. I mean, right? You got to type this in your graphing calculator. Watch your 3/2. You might need that in parentheses. You need this in parentheses. You can type it in like that, but that's more embedded parentheses. But anyway, if you type in the curvature function and graph it on a graphing calculator, I want to show you what you'd get for this one. You would get this. Well, actually, I'm not sure how high to go, but it goes up to 6. I mean, we know that. The curvature is 6 at that place. But this is what it's doing. It has maximum curvature. It has maximum curvature at that point. And way down here, look, what's the curvature on this very straight leg of the parabola? What's the curvature on this very straight leg of the parabola? Practically nothing. So the curvature kind of reaches its peak right in the curvy part here, and it reaches a peak right there. But I'm saying everywhere else on this curve, the curvature is approaching 0. I mean, the curvature is practically 0 on these very straight parts of this curve. Cool. I think I'm done. Yeah. And it's time to be done. Class is over. So that was good. That was just a nice